Okay, good morning. My name is Lei FAN from Beihang University, and it's my pleasure to represent my team to have this presentation. I would like to introduce our software, GSTAR, a new framework for processing geodetic data at the observation level. First is the background and motivation. An integration of geodetic techniques such as GNSS, VLBI, DORIS, SR, and intersectional link ICL helps to improve the accuracy of geodetic parameters. These parameters include geometric, Earth orientation, and gravity. They are essential for the study of Earth system change. At the present, the geodetic data fusion is mostly done on the norm equation level. A more rigorous way is to process the data at the observation level. Although this approach has already been performed, but it has not been fully exploited. And we know that an accurate and stable reference frame is the precondition of the Earth system study. An objective of the GGOS is to realize the ideal RF with an accuracy of 1 mm and a stability of 0.1 mm per year. And this requires the collocation of different techniques. Different techniques are generally combined according to the collocation sites on the ground. An obvious trend is to realize collocation of different techniques in the space. A typical example is the GNSS mission. It plans to carry out 4 geodetic techniques on board. So it allows for the first time a link between the ITF and the ICF. Another challenge comes from the increased number of the sensors. For example, the ground stations may reach tens of thousands, while thousands of satellites may walk into space. This will create tens of millions of parameters to be estimated. This is a big challenge for the geodetic software in terms of computation efficiency. This is because all these parameters are highly related. The computation efficiency cannot be significantly improved by just using more computers. So a new powerful software needs to be developed to process so much data with high performance computation. To meet the above challenges, we developed the GSTAR software, so let me briefly introduce it. The layered modular architecture is adopted in the GSTAR software. All modules are implemented using the object-oriented programming with the rule of high cohesion and low coupling. At present, there are more than 100,000 lines of C++ code. The advantage of this architecture is to realize the software in a modular form. So the developers will find it convenient for the secondary development by using a few interfaces. It also supports multi-thread processing using CPU and GPU, and it has good cross-platform ability on Windows, Linux, and Mac OS. When we design the data structure, we consider that the future satellite is assumed to have a number of sensors on board, for example, the GNSS satellites. So the antenna is taken as the core unit for data storage and processing. The antenna is designed as the base class with 4 interfaces, so developers can implement these interfaces in terms of different techniques. All antennas are independent with each other, so data in each antenna can process in parallel. And after that, the data are organized in 2 groups, namely parameters and observation minus calculation measurements, and they will be put to the estimator for parameter estimation. Now, the 2 types of estimators are realized in the GSTAR software. The first one is LSQ estimator for cost analysis, and the other one is the SRIF estimator for the real-time process. For the estimator, a set of rapid data processing algorithms are proposed. First, the automatic parameter organization algorithm is proposed to reduce memory and disk operations when time-dependent parameters need to be pre-eliminated. Second, sequential least square method based on CPU and GPU parallel algorithm is proposed, which includes high-performance linear algebra libraries, for example, BLAS for CPU and QBLAS for GPU. And also different steps in sequential least squares procedure and the input-output operations on disk and memory are conducted in parallel. This is a test for the processing efficiency in GSTAR. The example is a PLD procedure with 116 stations and with the interval of 5 minutes. This figure shows the results. The horizontal axis refers to the different combination of the satellite systems, and the vertical axis refers to elapsed time. And the traditional efficient algorithm used in Panda software is used to be compared. You can see that when all the 4 satellite systems are used, the CPU-based parallel algorithm costs about 40 minutes, which is about 6 times that used in the traditional one. And when the CPU and the GPU, both CPU and GPU are used, the GSTAR costs 25 minutes, about 9 times that used in the traditional one. You can see that it's a great improvement. But I think it is not an ideal result because the communication consumption between CPU and GPU is still a major problem which prevents further improvements. So a lot of effort needs to be made to make the biggest effect of the GPU. Okay, this page summarizes the function status of the GSTAR. It supports the combination of the GNSS, ISL, SR at the observation level, while the VLBI, DORIS, and the gravity field are still under development and test. And it supports of estimation of site coordinates and the satellite orbit and clocks, and geodetic parameters include ERP, geocenter, and atmosphere delay. Okay, next let me introduce the initial performance of the GNSS-based products from the GSTAR software. This table gives the strategy. More than 4 years multi-GNSS data connected from totally 315 stations are used for data processing. Before July 2022, the reference frame is aligned to IGS 14, and after that, IGS 20. The satellite clock is first estimated using 165 stations with an interval of 5 minutes. Then satellite clock is estimated using 100 stations with an interval of 13 seconds. After that, precise positioning procedure is conducted to calculate station coordinates using 115 stations. In addition, geocenter motion is determined independently with no net transmission and no net rotation constraint with using 100 stations. This is the GNSS satellite orbit results. ESA's products are taken as the reference, and all results are compared to it. Results from the GSTAR is denoted as BUAA, abbreviation of Beihang University. For comparison, the products from 7 IGS are also given. The left figure shows the RMS of each component for 4 years, and the right figure shows the time series of 3D RMS of each day. The red bar and the dots represent our results, while the other colors refers to IGS. And we can see that the difference between our results and the other ACs are very small. And this is the GNSS satellite clock results. It is evaluated by the standard deviation with respect to the ESA's product. Similarly, the red bar and plots represent our results, and it shows our position compared to other ACs. This is the station coordinate results. Our results are compared to the IGS daily solution. Helmholtz transformation is conducted to eliminate the frame differences of different solutions. We can see that the horizontal direction of less than 2 millimeters and up direction of less than 4 millimeters can be achieved in GPS-only solution by the GSTAR. This is at the same level with other AC solution. For Galileo-only and Beidou-only solution, the horizontal direction of less than 3 millimeters and up direction of less than 6 millimeters are obtained. This is the geocenter results. Time series of GPS, Galileo, Beidou, and the IGS products are given here. Also, amplitude spectra of each series are given in the right picture. We can see that the X and Y directions from different systems are consistent with IGS products. But for Beidou, some different phenomena can be found. The jacketic harmonics of Beidou 3 in Z direction are significant with amplitude of 19 millimeters. And the 7-day periodical signal are observed in X and Y directions. This might relate to the constellation geometry and the SPR models. Next, let me briefly introduce the evaluation of multiple geodetic data processing at the observation level for the geocenter. This is the combination of Galileo and the SR results. And the left figure shows the former arrow's time series as a function of the absolute value of the sun elevation angle, and the right figure shows the corresponding amplitude spectrum. Compared to the Galileo Omni solution with a small amount of SR, this is a mistake here, this should be SR. Yeah. The former error in the three directions is reduced by an average of 31%, and the third geodetic signals in the Z component is reduced by 17.4%. The inter-satellite link also contributes to the improvement of the geocenter estimates. When both beta 3 and the ISL data are used, the former error of the geocenter is reduced by 26% in the X and the Y directions, and 58% in the Z direction. The correlation between the geocenter Z direction and the SPR parameters is significantly reduced from 0.7 to 0.3. Okay, this is the summary. It is noted that due to the time limitation, some results are not given in this presentation. For example, the combination of Lei satellites and the result of atmosphere delays, and also the multi-frequency processing GNSS data. So also the GSTAR software is a newly developed software. It is still under development and it needs more tests. For example, the VLBI, DORIS, and the gravity field should be tested in the future. And we also plan to set up a website to provide open service for geodesy communities, and the user manual is expected to be finished soon. Okay, that's all. Thanks for your attention, and look forward to your questions.